Okay, so we can solve this equation for this vi of t that we have done already. Okay, so let's consider you are in some initial state at t naught. Okay, so you can work out this differential equation. So and figure out the solution. This I have already done. So vi of t I can write as 1 minus I by h cross. Okay. So you are evolving from some initial time t naught, okay, to t. Okay, so then you are going to dt prime di of t prime plus minus I by h cross square. Okay, so t naught to t dt prime, then t naught to t prime dt double prime okay, plus all higher order terms. Okay, so we have also seen we can express this in terms of time ordering objective exponential like this thing. This I can put as like this thing, chronological time ordering tau. Okay, that is your ordering time in the decreasing order from right to left, or the increasing order from left to right. Okay, so that's equal to minus I by cross t into t dt prime. So these are changes. These are all. Wait a second. So it is something like sorry. So you can write some time evolution operator in the interaction picture. Let me call that as a ui of t here. Clear? So ui of t is actually the solution of this very equation. So that is okay. So let me write it again. So it's like this thing. So you can put this equation in the operator form, d by dt of some ui. Let's not put like this. Vi tilde. Okay. Clear? So this you can write u. Okay, ui is the evolution operator in the interaction picture. Okay. So ui simply if you active ui on an initial state, it will evolve to the final state in the interaction picture that we are going to see. Okay, so this we can write as a time ordering exponential. This I have already told you what it means. Okay, like this. So it means simply you time order. So here you are having only one factor containing time, but you are having here how many factors? 2 factors, and rest will contain many factors, 3 factors, and so on. Okay, so you have to apply the time ordering once you act this on some stage, because it is not a priori known to you whether t prime is greater than t double prime or t double prime is greater than t prime. Clear? So you apply simply time ordering operator, then act on a given state. Okay. So this series is sometimes, or this expansion is sometimes known as Dyson sum. Freeman F.J. Dyson, okay, who was a physicist. He died recently, I think because of COVID. Okay. So in 2020 he died. So he was a great physicist. Okay, he proved actually his main contribution is that he proved that the theories by Feynman, Tomonaga, and Schwinger, they are equivalent. So all of the three developed a theory for quantum electrodynamics. Okay, independent of each other, and it was actually Freeman Dyson who showed all the theories are equivalent. Clear? So, so let me, instead of writing these files, let me do a different kind of notation. Okay. So, okay. So now I have this expansion at hand. Clear? Okay. So let's assume at t. Okay. So at some initial time. Okay. So let's take at t equal to 0. Your initial state is I. Or let's write t equal to t naught. Okay, got it? So let me write it as initial state. So we need to calculate the transition probability. Clear? Okay. So for that matter, if I have to evaluate the transition probability for a particle moving from one state to the another state, I should know actually the final state as well. Clear? So given the initial state is there. So let's assume my particle is in this very state. Okay. Clear? Now what I need to calculate? I need to calculate what is the evolved state or what is the final state. Okay, for that matter, I will apply on this I t naught. Okay, so let me apply this ui of t. Okay, t naught like this, because I am explicitly introducing the initial timer t naught. Okay, so you can write here t naught as well. T naught. You can also write here t. There is no problem. Clear? So what you will get? I will get some another state. Let's say the state at time t. Okay, got it?
Yes, sir.
So this is the or you can put it as, okay, so let's write f. So f. So I am having at t equal to t final state something f t. So that means my initial state has evolved via this evolution operator to the final state. Clear? Okay. So can I write it this way? So I will take now the complete set of states of H naught. Since the Hamiltonian what we are given, it contains an exactly solvable part or the time independent part for which we know the eigenstates, clear? And the time dependent part, clear? So let's take the eigenbases from there. So call these as, okay, so let me introduce this completeness condition. So this is equal to identity. So ui t naught, okay, clear? So can I write it now this way? This final state is equal to summation over n. Let me write this, since this is a number, okay, so I'll put as a c n of t. First, so where your c n of t. So ultimately what I need to evaluate Cm. Clear?
Yes, sir.
So these are actually the transition amplitudes. The mod of Cn square will give me the transition probability that a particle is being found in the state n, or it makes a transition from state I to state n. Clear?
Yes, sir.
Got it? So and then you sum over all the transition probabilities. Okay, so that should give you the one. So if you take the mod of Cn square, because to consider the probabilities, okay, so you take this object and sum over n, what it should yield me? 1. Okay? Got it? Huh? So this is, if you remember in the last lecture, we just postulated that my phi of t or psi of t, okay, in the time dependent way, I write it in this fashion. Okay? So, and now we have figured out those Cn of t's, I can always express in terms of the expected. Okay, so this kind of matrix element. Clear? If you are having some initial state and some eigenstate n here. Got it? So now let's look at first, since we are dealing here with the interaction picture. Now let's try to ask the question, does the transition probability depend upon the picture we are using? So it should, okay, so physically it should not depend. So which formalism you are using, so you should get actually the same transition probability. Clear? So that we are going to show, but it is not necessarily a transition amplitude can be different. Okay, transition amplitude in one picture can be different than the other picture. Only the transition probability will remain same. Okay? Why we are actually interested in this transition probability? Because these are the measurable quantities. Got it? Probability, what we can measure. Actually, this it's not directly I am measuring the transition probability. What I actually measuring in a given process, that is known as scattering cross section. So those will take in the next, a couple of lectures. Okay, where we can show actually this scattering cross section is actually proportional to the transition probability. Clear? So if in a given process, if I know the transition probability of certain process, okay, so I can measure experimentally what is the scattering cross section. Clear? So in other words, I can measure the transition probability indirectly from the measurements of what? Scattering cross sections. In a given experiment, you are only measuring the scattering, scattering cross sections, and from there you can read up what is the transition probability. Clear? Okay, and this transition probability helps us to calculate, let's say, the decay rate. Let's say you are having an atom, okay, or an electron somewhere, and this electron makes transition from one state to the another state. If you know the transition probability per unit time, let's say, that means it is the rate at which it makes the transition. Okay, so what it should yield you? It should give you the lifetime of the particle in that very state. Clear? Got it? Okay. So, okay, so let's look at the interaction picture, how the interaction picture is related to the Schrodinger picture. So let's take the interaction picture cat at time t, okay? So this is related to the Schrodinger picture cat, anybody? E raised of I h naught t by h cross, let's take alpha t naught in the Schrodinger cat. You are having, okay, so we had this kind of notation, phi of t e raised for I h naught t by h cross, remember, and psi of t. Okay, so this we write for the Schrodinger picture, okay, and this is for the interaction picture. Okay, so this I can write as e raised for I h naught. Okay, so let me check whether sorry, not t at t, at some time t. Okay, we are making at some time t, you are having this thing. At t equal to 0, they should match. Let's put t equal to 0. Schrodinger cat and the interaction picture cat are the same. Clear? So this is like this. Okay, so I can now invoke this evolution operator. So it is ui of t. So, okay. So what should I write? What should I write? What should I write? Schrodinger. Okay. Clear? It is simply the evolution using the evolution operator. Clear? Okay. The definition what I have given there. Okay. So this I can write e raised for I h naught t by h cross u I of t t naught. Okay. So now this I can convert at some time t naught. I can convert it to the interaction picture cat. Clear? Using this kind of definition. So what it will be? So it will be simply e raised for minus I h naught t naught by h cross and alpha t naught in the interaction picture. Clear? So this is the definition at some time t. Now what is the time t here? It is t naught. Clear? So you just take it on this side. So it will be e raised for minus I. So that means I am having an initial interaction picture cat related to the final interaction picture cat. Clear? Got it? Okay. So now what you can write? Okay. So if you see, so let me write it as simply some ui tilde t t naught. Okay. This t naught. Clear? What is this u tilde? So it is something I h naught t by h cross u I t t naught e raised for minus I h naught. Let's put t naught equal to 0. That means our initial time is equal to 0. We start from t equal to 0. So what this factor is? This is not there. Clear? And if you see, it is the same thing what we have done earlier. You are having some evolution operator, and then this is the total evolution operator, and multiplied by this exponential factor. Clear? Got it? Okay. So this is how we write that. Okay. So now let's write these matrix elements. So sorry. This is not ui. It is u. Why we have written as ui? Anybody? This is u. This is actually the evolution in the Schrodinger picture. Look. So you should know evolution in the Schrodinger picture is given by this u of T. Clear? Is this? So we have put I means the interaction picture. You should at least differentiate things. So I want actually what this time dependent cat in the Schrodinger picture looks like. So it's in terms of this evolution operator. So I should not put I. So it's an error here. I'm sorry. Clear? So you put an augmented T not as well. Everybody? Huh? Okay. So what is our evolution operator now? It is this utility. Clear? Okay. So is there any? Yes. Okay. So now look here. So this is actually the evolution. This represents the evolution operator in the which picture? So it gives you, if you are having some initial state defined where in the interaction picture, so this operator will simply give you the evolution to get the final state. Clear? So now let's assume your initial state is I. Clear? Okay. And then let me take this u tilde T naught. So what this will do? It will simply take it to the final state. Let me call that state to be n. Clear? You start from some initial state to the final state. So what this will give me? This will simply give me the probability amplitude for a particle moving where? Evolving from state I to state n. Got it? So now let's write it. So okay. So I can write it as like this thing: e raised for I h naught p by h cross, then u t naught. Okay, e raised for minus I h naught T naught by h cross I. Clear? Got it? Okay. So what this gives me, since this is the eigenstate, we are taking these as the eigenstates of the Hamiltonian h naught. So it will give me e raised for I. Okay, e n t by h cross, and this will yield me e raised for minus I. Let's write it as e I t naught by h cross. Clear? And then you are having n u t naught, okay, I. Clear? So now look here. So what this object gives me, since u is the evolution operator in the Schrodinger picture, or you can call it as the Heisenberg picture as well, there is no problem. Okay, so this is an evolution operator. So it simply gives me the evolution from state I to state n. Clear? Got it? So in some picture. Clear? So let's call this as a Schrodinger picture. Now this will give me the transition amplitude in the interaction picture. Got it? So if you can see the transition amplitudes in two pictures are not same, because you are having this additional factor here, an oscillatory factor. Clear? So now if I calculate the probability, okay, transition probability in this picture, in the interaction picture, okay, so what that is? So mod of this is 1, and it will be simply mod of this. That means the transition amplitudes in both pictures are what? Same. Got it? So if you are calculating the probability from one, okay, from one perspective, it is the same thing as if you are calculating it in the other perspective. Clear? So that means, okay, so this kind of result helps us to understand a given problem from different perspectives. Okay, a problem can be solvable in one picture. It can be easily solved in one picture, but in certain cases, it can be solvable in the other picture. Got it? Okay. So now let's write this Cn of t, what we require. Okay. So this is our formula, the Cn of t. So it is n u I t naught, okay, and I. Clear? So I will not put explicitly t naught here. Eh? So this is our Cn of t. Clear? So our final state. So what is that equal to? Summation over n Cn of t. It's starting from where? I. Okay. You start from I and you reach to some state n. Got it? And for the time being, we are assuming only the discrete spectrum. We are going from a discrete level to a discrete level. Clear? Okay. Then I will take into account if we are having to continue. Okay. So now let's write this UI. So using the Dyson sum, what is our UI? So it is identity minus, yes, I by h cross. Then you are having this t naught to t dt prime b tilde I d prime. Then you are having, you can write it in this way, t naught to t dt prime, then some t naught to t prime, okay, dt double prime b I tilde t prime b I tilde t double prime, okay, plus 1. Then you are having this state at time t. Okay, let me write this t naught explicitly so that you don't get confused. Let me write this t naught explicitly. Clear? Okay, what I have done. So I have put an exponential in. I have made an expansion here. Clear? In which factors? In the powers of 1 by h cross. Clear? So we call this as a perturbative expansion. Clear? Got it? This V, okay, so if you remember this VI, okay, so I am having this Hamiltonian h of t, it's equal to h naught plus VT. Clear? So I can put some that factor, the lambda factor, lambda V of t. Okay, you can turn on and turn off the interaction or the perturbation. Clear? So that means you scale it by lambda. Clear? So let's write it lambda here. So it will be, this term will be lambda raised for 0. That means 0th order term. So it will be some term lambda because you are having only one V. What this term will be? Lambda square and so on. So if you see, it is actually the perturbative expansion of what? This Cn of t. That's what I said you earlier. We are not looking at the perturbative effects on the energy states. We are looking the perturbative effects are we are calculating perturbatively the transition amplitudes or the transition probabilities. Clear? Okay. So let's write it. So let me write the Cn of t then in this way. So I will put a Cn of 0. Okay. Okay. So let me write Cn of 0 plus Cn of 1 plus Cn of 2 plus dash. Clear? So what is our Cn of 0? Now tell me. So it is this n. Then you are having this identity, and then you are having that I t. So it means simply you are having delta ni. Clear? Got it? So now let's interpret this very result and forget it. Let's put, okay, so let's forget all other terms. So you are having only this delta ni. So if I put this n is equal to I, what it means? So let's say you are having state n is equal to I here and all other states here. Clear? Got it? So it means, so the particle will stay in its in the state I all the time. Clear? It means there is no effect of the interaction. Clear? So that means there is no interaction effects in this very term. Got it? So if I put lambda equal to 0, that means you don't have the perturbation at all. If you put lambda equal to 0, particle will always stay in the eigenstates of this h naught. Clear? Got it? Okay. So now let's take the Cn1. So that is the first order correction, which is very important correction. So let's write the Cn1 of t. So because it is a time dependent factor, I will put explicitly it is minus I by h cross. Now if you see, okay, so this very point, so you are expanding it in the lambda by h cross in the powers of 1 by h cross. Okay. So it's equal to, let me write some t naught to t, then you are having dt prime, you are having this very cat n, because v is an operator, so it's not a function, it's an operator, like this way. Then you are having this I. Clear? Okay. So this can be simplified a little bit. So it is t naught to t dt prime. So n. So this I can write as e raised for I h naught t, so prime by h cross, because you are having the argument to t prime. That's why you write it here. So you are having vi. It depends on time. Clear? So let's write it as v of t prime. So it is a tilde means interaction picture. Now it's not the interaction picture. It is the Hamiltonian what is given to you. Okay, e raised for minus I h naught t prime by h cross, and then you are having this I. Clear? Okay. So it is minus I by h cross t naught to t dt prime. Okay. So this h naught will act on this thing. It will give me e raised for I e and t prime by h cross. This will act on the other side. This is e raised for minus I ei t prime by h cross. Clear? Okay. So what remains here? N vi t prime and I. Got it? So let's call this object as VNIT. So that means it is simply the matrix element of the potential external perturbation, okay, in the states N and I. Clear? So it will simply give the, okay, so it is simply the transition from the state I to N. Got it? Okay. So you can also write, let me define now this omega Ni. Those are the Bohr frequencies. So it is En minus Ei by h cross. So therefore I can write this first order correction to the transition property. So it's minus I by h cross t naught to t dt prime e raised for I omega Ni t prime. Okay, then you are having this V and I. Clear? So memorize this very formula. Okay, so you should memorize this formula. So this is very important formula. So okay. So now let's go to the second order correction, then we'll take an example. So what is Cn2 now? So you are having second order correction, Cn2 T. So what is that equal to? So it's okay, minus I by h cross square. Okay, 0 t naught to t dt prime, t naught to t prime dt double prime. Then you are having this n vi tilde t prime vi tilde t double prime. Then you are having get at initial time. Got it? So now this, okay, I can write now, I can introduce a completeness condition here, summation over m here. The reason being, okay, so since this has an exponential, okay, so this object is equal to e raised for I h naught t by h cross and vi e raised for minus I h naught t prime by h cross. Clear? So this also contains the same thing. I want to take these exponentials out. Got it? Okay, that's why I will put this completeness condition here. Okay, so let me write. So it is my, okay, so it will be simply minus 1 by h cross square t naught to t dt prime. Okay, so t naught to t prime dt double prime summation over m. So it is n e raised for I h naught t prime by h cross. Then your hank is v I t prime e raised for minus I h naught t prime by h cross, and I will introduce m here. Then you are having from this very thing. So you are having it as e raised for I h naught t double prime by h cross. This very objective. Then you are having v I t double prime. Okay, and e raised for minus I h naught t double prime by h cross, and then you are having this I. Clear? Okay. So now what you are getting, you will be getting H naught EM from here and EM from here. So I will write it as a omega NM. Clear? And similarly, you will be getting M here, EM here, and you will be getting EI here. So it is double prime. Huh? Okay, so I will simply put it as minus 1 by extra square T naught T dt prime T naught T prime dt double prime summation over M. Okay, like this thing. E raised for I omega this N, then this M, and M. And what is the time? It is T prime. Then you write it as V matrix elements between N and M. Clear? Okay. Then you put this exponential factor e raised for I, this M, omega M, and then this I, and then V, this M, and this V. So there is a T. Clear? Now look here the symmetry. Huh? So look at this very formula. You are having one exponential and one this thing, first order perturbation, and in the second case, second order correction. So you are having two exponentials and two VS. Huh? And you see you have to put everything in the order. Huh? Okay, so that the matrix multiplication is done. Huh? Got it? Samajh aawa? Okay, and so on. You can go to the higher order corrections. Any question? Okay, so what is the transition probability I can write now? So therefore, I can write this transition probability from state I to, let's say, N. So it can be simply equal to Cn0 P, sorry, Cn1, Cn2 P. Okay, got it? Only these factors contain time dependence. Huh? Okay. Okay, so let's consider the types of perturbation we will be considering in our course. I mean, which are relevant to us. So there are two types of perturbation which are relevant. Okay, first is the constant perturbation. So you, yes? Any question? So what I mean by that, so you start with some Hamiltonian H0, clear? Okay? Okay, you start your particle described by some Hamiltonian. Let me take it as some T less or equal to T naught. So we'll assume this T naught equal to 0. Got it? So our Hamiltonian is like this thing. And you turn on the perturbation for some time. Let's say T greater than 0, you turn on the perturbation like this. And this V of T, it is simply constant. So it's a constant. Constant in time. Got it? So you put a constant field that is not varying in time. Okay? So these kind of, have you heard about Auger transitions? Are the internal transitions of the atom. So there are a certain kind of processes happening in the atoms. Let's say if you are having two electron system, okay, one electron, okay, you in two electron systems, if you pick up one electron, so this one electron, this first electron can always make transitions to the internal states, kicking out the electron. So because it, if you are having a two electron system, so one electron will always see the continuum of the states defined there. Got it? Okay, so let me give an example. In the helium atom auto-ionizes. You know that auto-ionization of helium atom? Have you heard it? Okay, so let me give a clue. So what is the energy of the hydrogen atom? So there is some number, clear? Minus 13.6 by n square electron volts. So let's forget about these numbers. That means energy is proportional to this 1 by n square. When n tends to infinity, what happens to the number of lines, they become closer and closer. Okay, so that means you have a continuum of the states. Okay, so now if you are having two electron system, so let's say if you are having two electron system, this energy is proportional to like this thing, n1 square plus n1 square, like this. There are certain numbers here. Okay, so let's say this is the principal quantum number of one electron and this is for the another electron. Okay, let me fix n1 is equal to 1. So n2 I can arbitrarily fix, so it can go from 0 to infinity. That means for every this n1 number, you are having a continuum of the states. So when you are having the available states, continuum of the states, what will happen to the electron? So it may possibly jump to those states. So it may make a transition to those very states. Okay, so you can think the field which this electron observes, it's actually a constant field. So you can think it as a constant Coulomb potential. Let's say, think of the helium atom. So does the field change? So it is a constant this Coulomb potential. Clear? So the electron always sees the Coulomb potential, but still it makes a transition to the continuum of the states. And this way it autoionizes. Clear? So I will take this example in detail, no issues. Got it? So so these constant perturbations are useful to understand these kind of phenomena. Got it? So you are having a transition in a given electron system or in a given atomic system. So an internal electron makes a transition to the another state just by emitting an electron. Clear? Those transitions you know as Auger transitions. Like these things. So I will take this in detail. This example. Another case are, so we are having these sinusoidal perturbations, or the harmonic perturbations. These are very useful. Okay, harmonic perturbation means you apply actually a sinusoidal field. Clear? Okay, so there are other kinds of perturbations as well that I will take. Okay, so I will tell you. So you can have this H of T. So you this H naught plus some harmonic potential. Okay, so let me write this V of T, where V of T it is simply equal to some, let's say A e raised for or some V e raised for I omega t plus V star e raised for minus I omega t for t greater than 0. Okay, so is this a harmonic case? So you can write it in terms of, let's say, real of this object, that is cosine of omega t or sine of omega t. Clear? Okay, so these kind of perturbations are useful in understanding the coupling between, the transitions, those are happened by the electromagnetic field. So if you are having, let's say, the radiation that is interacting with the matter, you can treat those kinds of interactions by these harmonic perturbations. Clear? Okay, so here is a very important assumption in dealing with these kind of perturbations. So you take a perturbation and apply it for certain time. Clear? Okay, so it maintains its nature for certain time. Let's say we apply this kind of perturbation for some finite time. Clear? Okay, so and it remains constant in that very finite time. Okay, similarly here. Now there are another kinds of perturbation where you move, where you perturb system slowly. Let's say you apply the perturbation, or you apply the outside field on a given system and vary that field slowly in time. Clear? We call those kinds of perturbations that the adiabatic perturbations are. The approximations involved in those things are known as adiabatic approximations. Clear? Another sort of perturbation is that simply abruptly hit the system. Okay? The suddenly, or what we call the sudden perturbations. Think of the delta function kind of perturbation. You are having, let's say, V of delta t, perturbation. So what it gives me? So it kicks the system at t equal to 0. Because at t equal to 0, there it is infinity. At t not equal to 0, it is 0. So you are suddenly perturbing the system. Okay. So let's put this kind of example. Let's say you are having a particle in a box. Clear? And let's say box is of width A. and you slowly increase the length of the system. Clear? So the perturbation dealing with this kind of system where you slowly expand the box is known as adiabatic perturbation or the adiabatic approximations. Clear? But if you suddenly move the system, okay, let's suddenly take system of size A to system of size B. Clear? Suddenly, okay, you suddenly increase the system. Clear? So what happens? So it is some sort of sudden, we call it as a sudden approximation. Clear? So these are nowadays, these are very important, these sudden approximations or sudden perturbations. There is a name for them, sudden, we call them as a conjured systems. Okay. Okay. Sudden, where you apply the sudden, perturbation, these are simply the, we call these as the conjured quantum systems. Okay. So these are actually topics of current research. Okay, because when you cool down the system, okay, so you can cool slowly, you can abruptly. Okay, and okay, so there is a lot of fun in dealing with these kind of systems. Okay, so let's take this constant perturbation. I will take the example of this conjured system later on. So think of a harmonic oscillator. You can think it this way. You are in a harmonic oscillator of frequency, let's say omega, and you suddenly change the frequency to omega. What will happen to the system? You are having a new system instead of the old system. Clear? And how the states will evolve. So then you can calculate the transition properties. So those are the questions you can ask. Okay. And the adiabatic this approximation was mostly developed by Landau himself. Okay. So now let's take this constant perturbation. Any time remaining?
10, 16.
Okay, so okay. So what is our perturbation? So this V of t, that's simply equal to constant for, let's say, 0. Okay, for t greater than 0. Okay, let's say t greater than 0. So you are having a constant perturbation. So what is our, let's calculate the first order correction. See, so that's equal to, so I will start from 0 to t, clear? So it is dt prime e raised for I ni. Okay, so t prime, then you are having v n I t. Okay, so now what is this v n I t prime? So that's simply equal to n, this v of t. So what is this v? So it's a constant thing. So it will be simply n v I. So that's simply a constant. Got it? So it's simply a constant thing. So if this is constant, you can plug it out of this integral. Got it? Okay. So which implies therefore the Cn1 of t, that is equal to minus I by h cross. So I will be having this v n I. Okay, now you don't put a time argument here, so it is independent of time. 0 to t dt prime e raised for I omega n I. So what is the value of this very integral? Okay, so it's e raised for I omega n I t minus 1 divided by I omega n. Clear? So this is the transition amplitude for a particle making transition to state I to state n. Got it? So therefore I can calculate this mod of Cn1 t square. So that gives me the transition probability from state I to n. Clear? Okay, so how much is that? So let's take this thing. So it will be mod of Vni square by h cross square, and mod of this very factor e raised for I omega ni t minus 1 divided by omega ni mod square. So if you take the mod square of this thing, it will be 2 minus twice cosine of omega t. Okay, So it will be simply mod of V n I square by h cross square. So it's 2 minus twice cosine of omega n I t. So just okay. So if you are not able to do it, so take this thing multiplied by its conjugate. Okay. Okay. So this is 1 minus cos. So that is sine square. So therefore I am having this p I to n of t. So that's equal to 4 times v n I square divided by h cross square. So it is sine square omega n I by 2 divided by omega n I square. Clear? So what is that omega n I? Just tell me what is omega n I? So it is sine square. So it is E n minus E I by h cross. Okay, twice h cross. Okay, t divided by E n minus E I. Okay, so this will not be there then. Clear? Isha? So this is magnitude, huh? So I'm sorry, this is a magnitude square. So this is a magnitude square. Because it can be negative, huh? Clear? So it is a magnitude square, you should know it. So now look here. So what is the transition probability? First thing you should know, this transition probability should be smaller than 1. If it exceeds 1, then it's a problem. Clear? And it should not approach to 1. Okay? So it should be very smaller than 1. Why? Because we are picking up only one term, only first order correction to the transition amplitude or transition probability. Clear? And the sum over all those corrections should yield me 1. Got it? Okay, so this is the first point. Okay, and second thing, it is oscillating in time. Okay, you can check it. Because you are having a time dependence here. Eh? Okay, so what is the maximum? Okay, so you are having, let's plot it. So this is omega n I, and then you are having, let's see, this is your p I to n of t. Okay, so at t equal to 0, you are having 0. So that means state is initially in some state. Okay, what will be the maximum here? So it will grow to the maximum. Okay, then it will go. So what will be the value here? So at what time? Since at what value of omega it should go to 0? Just tell me.
Ground state En is equal to Ei.
At what value? 2 pi by omega n I. So if I use 2 pi by omega n I for this t, it will be 0. Clear? So what is the maximum value? So obviously maximum. Okay, so maximum value is not 1 because sine square goes to 1. Clear? What is the maximum value? Just tell me. So it is something 4 mod of n I square divided by E n minus E I mod square. Clear? So this is the maximum value. Huh? So then it will go to this minimum value 0. Then it will. So you are having this as the oscillating. So what is this value? Anybody? So at what value? So this is 0. So what is this value? 5. Got it? So let's stop here. Then we'll do something more on it. Okay, yes, one point. So this only does not depend on time. So this probability depends on the magnitude of this VNI square. Clear? So this is one point. Another main point is it depends on actually the difference of the energies. Okay, so let's say if EI goes to EM, so if they are the same, so it is infinity, but it's not infinity. You are having this factor here as well. So we need to take those kinds of limits in detail. So that I will take tomorrow. Okay, so we'll do it.